Hi, welcome back. So, this is lecture 53 in this course, and the topic of this lecture is Bayes factor implementation. Okay. In the previous lecture, we discussed that what is Bayes factor and how Bayes factor analysis can be used to quantify evidence for a model compared to some another model. Okay. And the idea was that you can compute the ratio of marginal likelihoods. So, let us say you want to compare model 1 and model 2, you can compute Bayes factor in favor of model 1 over model 2 as the ratio of marginal likelihoods of model 1 and model 2. And why? Because we saw that evidence that how likely is a model given the data. Okay. So, basically probability of model 1 given the data against and with respect to probability of choosing model 2 given the data can be given by marginal likelihood of model 1 divided by marginal likelihood of model 2. We derived this relationship using Bayes theorem, because according to Bayes theorem this ratio would become probability of data, probability of this data being generated by model 1 into prior probability of model 1 divided by probability of generating data by model 2 into prior probability of model 2. So, this term is actually your marginal likelihood. This is prior probability of model 1 and model 2, which we assume that their prior probabilities are equal. So, we do not have any prior bias about any of these models. So, it essentially reduces to ratio of marginal likelihoods of two models. This ratio of marginal likelihoods is called the Bayes factor. This Bayes factor gives us a quantification of how much evidence is there in favor of model 1 compared to model 2 given the data. Okay. So, if Bayes factor is greater than 1, that means model 1 is more likely given this data compared to model 2. If Bayes factor is less than 1, that means model 2 is more likely, and that is the interpretation of Bayes factor. Now, the question is, how do we compute marginal likelihoods? Because once we know marginal likelihoods, we can take their ratio and compute the Bayes factor. But how do we compute marginal likelihood of a model given the data? So, what is marginal likelihood? Marginal likelihood is integration of likelihood and prior density of theta with respect to theta. This is the marginal likelihood. And we know from what we talked previously that this is very difficult. It is very difficult to compute this integration, especially when you have non-conjugate priors. Okay. In that case, it could be the situation that your integration, this function is not integratable at all. So, what we do in this situation? How do we calculate the marginal likelihood? We need to solve this integration. So, what we do some sort of approximation of this integration, and one kind of approximation that we discussed is called Monte Carlo integration. How does it work? It works like this. You draw a lot of samples from some importance density, let us say g of theta. Now, you calculate likelihood for each theta j and prior density for each theta j and divide it by importance density of theta j, and you take expected value over all these likelihood into priors. Okay. So, basically it is the average of likelihood into priors divided by this importance density, such that all these samples are coming from the importance density. So, this would give a reasonable approximation of the marginal likelihood if this n is large enough. That is the idea. So, you can use this to approximate the marginal likelihood. Of course, for conjugate prior cases, you will have analytical solution of the marginal likelihood, but for non-conjugate cases, you will have to do some computational, you have to use some computational method to get this marginal likelihood. Okay. There is also a package in R called bridge sampling package that you can directly use to calculate Bayes factor. Okay. This method uses a version of Monte Carlo integration, much sophisticated version of Monte Carlo integration, but does basically the similar thing. Okay. This is fine. Now, let us take an example and let us try to implement this Bayes factor analysis in R. That how do we do for some practical example. Okay. And I will illustrate one more fact using the example that Bayes factor is highly sensitive to the prior, to the priors on the parameters of interest. So, as you change priors, Bayes factors can drastically change. That is an important point, because the kind of measure we are using here for model comparison, this measure Bayes factor actually relies on the prior predictions of the model. So, that is why this is very different from ELPD or basically cross validation, which uses expected log predictive density. What happens in expected log predictive density? What kind of predictive density it is? It is actually posterior predictive density. Okay. So, once the model is already trained on some data, how well it can predict future data. But here we are not training the model on some training data. We are directly evaluating whether prior predictions of the model are close to the data. So, this method Bayes factor analysis is based on prior predictions of the model, and cross validation or ELPD based methods are using posterior predictions of the model. So, that is why of course, any posterior predictive measure would be less sensitive to the priors, because you have already trained the model on some data. So, using the posterior, not the prior, to generate future predictions, but here you are generating future predictions based on the prior. So, if prior is really wild, let us say prior is allowing lot of variability, then your future predictions are going to be noisy. So, that would affect how good is your model, right, which is not the case with posterior predictions. So, that is why Bayes factors are highly sensitive to the choice of priors on the parameters of interest. So, that is why evidence for a model will be conditional on what kind of priors you are choosing for the parameters of interest. Okay. And we will see how. So, to illustrate this, we are going to take a simple example. So, we can take more interesting hypothesis testing example, but let me begin with a much simpler version. So, let us say you are interested in modeling the number of road accidents in a day in Kanpur. So, your model wants to predict how many road accidents would occur in a day in Kanpur. Okay. This is the data you have from previous 5 days, that how many road accidents occurred in Kanpur on last 5 days. Okay. So, let us say these numbers are 10, 15, 20, 5, 11. Okay. So, these are road accidents on last 5 days in the city. Okay. Right. So, these are the number of road accidents that occurred in a city on last 5 days. Okay. And our goal is to model this. Okay. So, let us just first write the likelihood assumption and prior assumptions. So, we want to specify our model first. But we have two models here, we want to do model comparison. So, let us say model 1 has these assumptions. So, the likelihood assumption is like this: the number of road accidents on ith day comes from a Poisson process with underlying rate parameter lambda. So, lambda is the rate of road accidents in the city, where lambda, so this is a prior assumption. Okay. You know, this is the likelihood assumption, and now we are going to write the prior assumption. So, the prior assumption about lambda is that it comes from, let us say, gamma tan 1. Okay. So, this is model 1, and let us say model 2 is yi comes from Poisson lambda, but on lambda the prior is 10 10. Okay. So, these are your two models. So, these models differ. The only difference, what is the only difference between these two models? The prior assumption. These two models differ in their prior assumptions about the parameter lambda. Okay. Now, let us work with this. Now, we want to compute base factor for model 1 over model 2, right. So, basically we want to compute marginal likelihood of model 1, marginal likelihood of model 2 and then take their ratio. So, how do we compute the marginal likelihood? So, let us use Monte Carlo integration. Let us use a simple Monte Carlo integration method. Okay. So, let me create a function MCI, which means Monte Carlo integration. This function would take, let us say, how many iterations or how many samples you want to evaluate. Okay. And let us not create function. Let us go without function. I think that would be fine. So, let us say number of samples you want to evaluate is, there should be actually large number, otherwise you won't get stable base factors. So, let us say I decided 1 lakh samples. Okay, you should have at least 1 lakh, otherwise it won't work. It would work, but you won't get stable base factors. That means if you do this process again, you would get a different marginal likelihood. Okay, what are we going to do? We can run a loop from I in 1 to number of samples. Okay, and in each iteration we would generate a proposal. Okay, so we'll generate a proposal lambda. Okay, let us call it lambda I. From where? From some importance density. So let us say the importance density is that's a truncated normal. Okay, do we also have trunk norm? Truncated normal is fine. So let's say proposal density is truncated normal. So we'll generate why truncated normal, by the way. We want to generate lambda from a normal density. That is fine. This is just my choice. I'm choosing some Gaussian density to generate my proposals. This is my importance density. But why truncated? Because lambda cannot be less than 0, right? Lambda has to be greater than 0. So we need to take into account that constraint. So let's say I will generate one proposal from this density with mu, let's say around 50, could be 0 as well. Let's say 0. SD would be, let's say 50. So I'm allowing lambda values to be between 0 and 100 approximately. Okay, if you want to allow higher values than SD 100, it is also fine. Then lower bound. So let's say lower bound is 0 and upper bound is infinite. So that would give me 1 lambda value, basically one proposal for lambda. Now I will perform MCI here. So basically I will calculate likelihood into prior and divide it by proposal density. So what would be likelihood? Likelihood will be d poise y given lambda I, and y has multiple data points, so we can calculate joint likelihood, product of all these indivisible likelihoods. Then we can calculate prior. Prior would be d gamma. Now this is for model 1. For model 1, the prior is d gamma lambda I and tan 1. Model 1 says that a prior is gamma tan 1, and importance density will be d norm. You should use d trunk norm, but I do not think I have function for d trunk norm in this package. So, I am just using d norm for simplicity, but you should use d trunk norm because we want density from truncated normal distribution. In this case, if you just divide it by 2, I think divided by half, you will get the same density. So, if you just multiply 2 into d norm density of obtaining probability density of obtaining lambda I when mu is 0, st is 100, lower bound is 0, upper bound is infinity, you will get the same thing. So, everything is fine so far. We have got likelihood, prior, importance density. Now, I can compute, basically I can store some term, let us call it weighted likelihoods. This is likelihood into prior divided by importance density. Okay. Basically, I am storing likelihood into prior for each proposal. Okay. And in the end, once I get this vector, I can take average of this vector. That would be approximate marginal likelihood for model 1. Okay. So, let me run this. Okay. So, these are unused arguments here. Okay. So, marginal likelihood of model 1 is given by mean of these weighted likelihood values. Three into e to the power minus 8. Okay, it's a low value. Now, let us calculate the same for model 2. Everything else would remain the same. The prior changes for model 2, the prior is different. It's prior, okay, lambda I 10. Okay, this would be ml for model 2. Okay. Now, let us calculate base factor for model 2, sorry, for model 1 compared to model 2. So, that would be marginal likelihood of M1 divided by marginal likelihood of M2. This is my base factor. So, this base factor will tell me amount of evidence for model 1 compared to model 2, and this evidence is actually quite high, e to the power 18, 10 to the power 18. So, basically it is a very large value. Okay, so, there is strong evidence in favor of model 1 compared to model 2, and it makes sense because the kind of prior model 2 uses gamma 10, it restricts the lambda values to be between 0 and 2, okay, and the data says the otherwise, right. So, this model is actually not a good model because it makes a strong prior assumption that the rate of road accidents is somewhere between 0 and 2. So, this is that is why this is not good. This is good because this allows the lambda values to be between, let us say, around 5 and 50 or so, right. So, this is fine, but this is too strict prior, that is why this is not a good model, and that shows up in the base factor. Yeah. In fact, you can try more. So, let us say what if you have another model which has prior gamma 10 2. Now, this is not very different prior, okay, and it could be the case that both these models would have similar marginal likelihood. So, it could be the case that model 1 does not have strong evidence compared to model 2. Let us see. So, what we want to change 10 2. Okay. So, let us see. So, 53. Okay. So, now the evidence is not that strong as we had earlier, right? It is just 53. Okay. And when it is even more close, let us say gamma 1.2. Okay. Now, the prior is almost same. So, let us see what the base factor would tell us. Okay, we did not change it here. What happened? Okay. Now, the base factor is 1.62. Okay. So, basically slightly higher. So, base factor for model 1 is slightly higher than model 2, but not strong enough. So, base factor is 1.62. So, the convention is that if the base factor is between 1 and 3, there is actually some anecdotal evidence for model 1 compared to model 2. So, you should not rely, so you should not basically take base factor between 1 and 3 seriously. Okay. That could be, I mean, that much evidence could happen even due to, let us say, when you have less number of iterations, base factor are not stable. So, it can give different values, right. So, anything between 1 and 3 it's called anecdotal evidence. Anything between 3 and 10 you can say there is weak evidence or moderate evidence. Anything above 10 is strong evidence, right. So, in this case you have anecdotal evidence. One interesting thing you can observe is that if you run the same code again and you compute the same base factor again exactly for same example with same model and with same data, you would see a slightly different base factor. Why? Because we are doing Monte Carlo integration, it is an approximation. So, it is not going to give you exactly same value, it will be slightly different. Okay. And let us try some example where you can consider some hypothesis testing. Okay. So, let us try something within this. So, let us say model 1 assumes that lambda is equal to exponent of alpha plus beta into vacation I, okay, whether ith day is a vacation day or not. Okay. So, let us say if it is a weekend, then there would be less traffic, so less rate of road accidents. If it is a work day, there could be more accidents. So, whether ith day is a vacation day or not. So, its values could be 0 1 0 1. Okay. So, we can write it like this, we can create a variable, independent variable vacation, right, which has values like 0 1 1 0 0, okay, for 5 days. So, this is what model 1 assumes, that lambda, the rate of road accidents, depends on whether it is a vacation day or not. Okay. So, now the parameters have changed, you have two parameters alpha and beta. So, let us say alpha has this prior gamma tan 1 and beta has this prior normal 0 5. Okay. And for model 2, so model 2 has same structure. Okay, lambda depends on alpha plus beta into vacation, so it's a function of vacation, but prior on gamma is alpha is also same, but beta is assumed to be 0, exactly 0. What does this imply? That model 2 assumes that there is no effect of vacation on the rate of road accidents. So, rate of road accidents would depend entirely on alpha. By the way, this gamma prior is not very good. So, you should think about what would be log 10. So, that should be the range of alpha. Okay. So, let us think what would be log 10, log 10, log 15, right. Yes, so somewhere around, let's say 2.5. So, what we can choose as a prior is normal 2 2, okay, and this could be normal 0 1. Okay. So, alpha could be normal 2 2 and beta will be 0. Okay. But what does this imply? Beta equals to 0, that model 2 assumes that there is no effect of vacation on the rate of road accidents. Model 1 assumes that there is some effect of vacation on the rate of road accidents. Okay. These models are implementing two competing hypotheses. So, model 1 is implementing this hypothesis that vacation affects road accidents. Vacation affects the number of road accidents. Model 2 is assuming that the vacation does not affect road accidents. In order to test which hypothesis is correct, in order to quantify evidence for this hypothesis, the vacation effect hypothesis, you need to compute base factor for model 1 compared to model 2, because model 1 assumes that beta has non-zero value, beta can have non-zero value, model 2 assumes that beta has value 0. You can also call this one as the null hypothesis model and this one as the vacation effect model. Okay. Now, you can compute base factor by calculating marginal likelihood of model 1, marginal likelihood of model 2 and take their ratio. That would give you base factor for model 1, and that base factor value is giving you amount of evidence for the vacation effect compared to the null hypothesis. Okay. So, that is how we can test a hypothesis of interest using base factors. Okay. Now, we will actually implement these two models to calculate their marginal likelihood using Monte Carlo integration in R in the next lecture. So, we will compute marginal likelihood for each model, model 1 and model 2 in R, and we will see that how much evidence is there for model 1 compared to model 2. Okay. And we will also see how these base factors are sensitive to the choice of our priors on this parameter beta for model 1. Okay. All right. So, in the next lecture, we will take this simple example and see how base factor works for hypothesis testing, how base factor can be used for hypothesis testing. All right. Thank you very much. I will stop here.